Hi, my name is Manikanda Sriram. In today's video, I will be showing you how to build a LEGO two-wheel self-balancing robot using the Mindstorm's NXT kit. So, this is a very popular experiment. It has been done many times before. The first of this was done with the first version of Mindstorm's kit, which is RCX. It was called Legway, and now in NXT it is called NXT Way, and you can see in the bottom of the screen NXT Way GS, and GS stands for gyro sensor, which is a sensor used in this experiment. So let me show you the robot. So this is the robot. As you can see, there are two wheels and two motors, and in the center we have the NXT brick. If you look at the back, you have the sensor over here. This is the gyroscope sensor, which has one axis of sensing. It can sense the pitch of the bot, and we have connected it to port number 3, and we have connected the motors as well. So this is the bot which we are going to control. We are going to write the code to make it balance on its wheels. So coming back to the presentation, as I have already told you, we will be using the Simulink programming environment for developing the code. So before we start with programming, first we must get a mathematical model of the system that we are going to use. So here I have the perspective view, top view and the side view. So these are the different variables which will be used in this program. So theta L and theta R correspond to the rotation made by the left and the right wheels. So R times theta, where theta is in radians, is a measure of how much the left wheel has moved and how much the right wheel has moved. So on average we can consider that the robot has moved forward by R times theta, where theta is average of theta L and theta R. And in similar manner we have psi, which is the body pitch angle, and we have phi, which is the yaw angle. So the theta, phi and psi are our three generalized coordinates which we will be using in the simulation and in the building of our control system. So we can write the equations of motions for it. I have left out the details. You can find all the details in a very detailed documentation available, and so if you write the Euler-Lagrange equations, where the generalized coordinates we have taken are theta, phi and psi, you will be able to get the state equations of the system. So this is the linearized state equations, wherein I have linearized the system about the equilibrium point psi equal to 0. Inherently the system is nonlinear, where it has the psi dot square and phi dot square terms, but since we would like to make our system simple to make it easier for us to handle the system, we have linearized it about the equilibrium point. So this gives us the three equations. An interesting thing to note over here is that the first two equations are independent of phi, and the third equation is independent of both theta and psi. So noting this, we consider our state variables as x1 and x2, where x1 is theta psi theta dot psi dot, and x2 is phi and phi dot. So this gives us a state space representation of the system. You must be familiar with this notation, and u is the input to the system. In this case it is the voltage applied to the left and the right wheels. So this voltage that we apply maps to how much the theta dot of that particular wheel. So now we have a mathematical model of our system, and we can proceed with designing a controller. So this is the overall controller diagram. It is a block diagram of the system. So as you can see, the controller we have used in this case is a servo controller, and there are different types of controllers we can use, but in this case we are using state feedback, and so we generate the reference state which we want to achieve, that is x1 ref, and from the system we take sensor readings and construct the current state the system is in, and using that we form a feedback loop. In this case, C theta is just a matrix to obtain theta from x1. So, theta is our first row in x1. So, it is just a matrix to extract out the desired theta value. And as you can see, there are two loops here. One loop is with kf, wherein you have x1 ref minus x1. So, this is the state feedback, and kf is the feedback gain. And to this we add another loop which comes from theta. So, theta ref minus theta, and so what is theta? Theta in our case is a measure of how much the bot has moved in a linearly translated. So, what we are trying to do here is we are having an integral controller, which implies that we are trying to track our desired theta. That is, we not only try to stabilize the bot about the equilibrium point, we also ensure that it does not drift away from its initial starting position. So, now that I have shown you the general block diagram, let us see how this has been programmed in Simulink. So, this example code, this code is available by default in Simulink when you install the hardware package. So, you can find it from the library. Let me show you. So, as you can see over here. So, it is the same as this. So, over here we have the overall block diagram, that is, we have the controller and the hardware. This particular model combines both a simulation environment and implementing the code on the actual hardware. So, if you use deploy to hardware, it will take data from the actual sensor signals, while if you use a simulation environment, it will simulate the system using a model. So, let me start with the hardware. So, these are the sensor blocks, these are available in the library. So, we are taking the time, the right wheel encoder, left wheel encoder, and the gyro reading and the battery reading, and here is just a filter to remove the noise in battery readings. So, this gives us our actual sensor signals, and right now let us not worry about what is happening in the top. It is basically, instead of having the hardware, we are trying to simulate the same thing using a model. So, the input to this subsystem is the right wheel speed and the left wheel speed, which are being applied to the motors. So, tracing where the sensor signals are going, we take into the controller. There are two inputs over here which are of interest, the speed and turn angle. So, what this says is that this is our external, we can use this to command the bot to have a specific behavior while still maintaining balance. That is, if I give a speed of 1 meter per second, it would mean that it will have to stabilize, but at the same time move forward. That is, it should not fall down, but it should move forward with a specific speed. In the same way, turn angle implies that it should keep turning while still not falling down. So, these are the three inputs to the controller. If I open, so there are different parts to it. So, the first thing is the gyro calibration. This block just implies that this is active during the initial 4 seconds. So, the first 4 seconds is used for gyro calibration. So, what is gyro calibration? A gyro sensor does not directly give you only the rate of change of angle. It gives that value about a mean value. So, say suppose by default, if you connect your gyro sensor to your system, say it gives you a value of 40. So, the value 40 does not mean it is turning at 40 radians per second. it could be the mean value, and so for even when the body is at rest, it will give 40, and if the body starts tipping, then it will give 41 or 42. That is, 40 is the mean value and the actual value is with respect to 40. So we first have to calculate what is the gyro offset. So what we are doing here is taking a moving average for first 4 seconds. So we are taking continuously reading the data and taking the overall average of it, and this is just to for us to know when the gyro calibration ends. So as long as the gyro calibration is happening, you will have a constant tone that the NXT bot will keep playing. So this 1 by z denotes delay of one sample. So you have 1 minus a times the new sample plus a times the old sample, which is implementing the moving average. So once you have this, this is your gyro offset, and this is your current gyro reading, and the speed and turn angle are the commands that we are giving, right wheel and left wheel rotation from the sensors, and battery also from the sensor. So moving on, let me start with the calibration reference in this subsystem. So what you are having is you are taking the speed and the turn reference, turn angle. These are commands, and with this we form this reference state, that is the state that we want to achieve. So here the speed determines what my theta dot reference must be, and if I am just having a discrete integrator to give my theta reference, and this psi reference implies that it must be erect, and psi dot means it must not fall down. So this is our reference state, and so coming back, we have our reference state theta ref and PWM term and x1 ref. X1 ref is our state, and the other block. So if you see over here, this calculates our current state. So the right wheel and left wheel rotation, the sensor readings are in degrees, so you are converting it to radians, and then so over here we are adding, so there is an addition block, and what we are adding is psi. So from the gyro value, we are subtracting the current gyro reading from the gyro offset, which gives you your tipping angle, and that is again in degrees per second. So you convert it into radians, and you have an integrator to give you your psi. If you notice over here, the theta reading that is given from the motor is added with psi. So that is your final theta L. So let me show you why this happens. So moving back to the model, as you can see over here, theta MLR, that is the motor left and right, that is the encoder readings, is this angle, while we are interested in theta LR, which is with respect to the erect position. So that is why theta L and LR is basically psi plus theta M. So that is what is being implemented over here, and we take the average of theta L and theta R to get our current theta value, and as we can see, we take the derivative of theta to get our theta dot, and psi dot we have obtained from the gyro sensor. So this gives us our current state. So if you see over here, you have the x1 ref and x1. So over here what we are implementing is the feedback loop for the inner loop. So let me show you the controller diagram again. So what we are implementing is over here is kf times x ref minus x. That is what is being implemented over here, and then over here you have theta ref minus theta, and this is the integral controller, that is, this is used for tracking. So this corresponds to this blocks over here, and we add this and we give it to the NXT way, that is this is our input that we must give to the motors. So for the next block, so we have our voltage that we must supply, and this is how we implement it on the system. So you want to apply some voltage, but in the NXT you cannot directly give what voltage to apply, you should instead give it as a PWM. So, again PWM is pulse width modulation. I have mentioned it in the first video. So, pulse width modulation, so what implies is that you have to give the duty cycle ratio, that is what percentage of the maximum voltage should I give. So, in this case we are therefore dividing the required voltage with the current maximum battery voltage. So, this you can see is derived from current battery reading. It is not a constant. That is because your battery voltage keeps varying, it will keep decreasing as you use it until you recharge again. So, as the battery voltage comes down, the maximum voltage that can be given to the motor also comes down. That is why you have a saturation box over here, which implies that you cannot have you cannot have more than 100 as the PWM that you supply to the motor. So, you have to restrict it between -100 and +100. And so, you have the PWM that has to be given a PWM turn, which I will come to, and theta r, theta l, and so let us go to the PID control. So, over here your input 1 is the voltage that must be given. Input 1 is the voltage and input 2 is the PWM turn. So, how we are implementing turning is by giving an additional voltage to the left wheel with respect to the right wheel. So, that is what is being implemented over here. The right wheel directly gets the PWM, whereas the left wheel gets an additional PWM based on the turn angle that we want. And you can see the saturation block I was talking about. So, a maximum is 100, minimum is -100. If you see over here for the right wheel, there is another block which is giving some additional PWM. So, what does this do? So, what are your inputs 3, 4 and 5? If we look at it, our input 3 is a phi dot command and 3 and 4 are your thetas. So, over here you have a loop which determines whether the bot is falling or not, and it determines whether your bot is turning or not. So, whenever you are turning, you do not want to synchronize the left and the right wheel, because that is how you turn. But when not turning, you want to synchronize your left and right wheel so that you move straight. This is because for a given motor, the voltage to PWM ratio is unique. So, if you take two motors, give the same voltage, you cannot expect them to move at the same speed. Therefore, even though you give the same PWM and you expect it to move at the same speed, it will not. So, you have an additional proportional controller which will ensure your left and the right wheels are moving in sync. So, that gives you the additional PWM, that is additional correction, let me say, that is being added to the right motor, and this is being fed to PWMR, and if you trace back, it is actually going to the hardware, and coming back you can see that it is actually being fed to the motors. So, this explains what is happening in the model. So, in a lot of places you saw that it has been used using variables like Kf. So, what is the value of Kf? How are these calculated? So, to explain this, you have to see where these values are declared. So, if you look at the model properties and go to callback, you will see that post load there are three statements which are being run after loading, that is there are three MATLAB commands. So, if you look at the folder, you see those relevant MATLAB files. So, what do these do? The LEGO self balance plant.m file, this declares all the values of the different parameters that are being used. So, let me show you the model. So, as you can see, there are different values, the W, H, D, everything are declared over here. So, if you scale up your module or if you change any parameter in your model that you have built, so you will have to correspondingly change the particular value in this file. So, with this, you form the A, B, and C and D of your state space representation. So you can refer the documentation for more detail on how these are obtained. So these are obtained from the state equations. So as a gist, I can show you that this is where you calculate your Kf and Ki. So these are pre-calculated for this particular model using LQR. So LQR is linear quadratic regulator. So if you are interested, you can there are a lot of books on optimal control which explain these topics. So if you want to tweak your controller, this is the file in which you have to do it. So now we have seen the controller. As I have mentioned, you saw that there is a proportional controller which is being used for wheel synchronization, and a rotation is being achieved by giving a biased voltage to the left wheel. So let me give you a small demonstration now. So I have already downloaded the code into the program, into the bot. So this is when the gyro calibration happens. So now the calibration is over, so I am leaving it. As you can see, the bot is balancing on its own. So even if I give a small disturbance, let me just tap it. So even though I give it a disturbance, it still settles back, and but one thing that you notice is that it never stands perfectly still. You must have heard of Segway, which stands perfectly still, but in this case it does not happen. The reason is that there is the sensor that we are using is not very precise. That is, until it starts tipping at considerable speed, it assumes that it is not tipping. So let me try adding some extra weight to it. So this was in the model with which you calculated the gains, but it still works. So you can intuitively understand this as the stability margin, like how much extra weight or how much can I shift the system from its actual from the design system, wherein the system still works. So how much force can it tolerate? So that was its margin. So this is just a small explanation, demonstration of. So let me make a radical change to the system. So I am going to change these wheels with the smaller wheels. So now we have changed the wheels to a smaller size. Let's see what happens. It still works, but as you can see, it's a lot more oscillatory. And let me try giving it a small nudge. As you saw, even for a small nudge, it fell down. So the reason is that this is not a system for which the feedback gains were calculated. So let me give a more rigorous test, but let me go back to the old set of wheels. So we have the system back again. So if we rerun it, we expect it to work like before. Okay, it works. So let me give it a more intense test. So let me try keeping a water bottle on top of it. Let's see if it can stabilize that. As you can see, it was able to do it for some time, but it's not able to sustain it because one reason is that the water bottle is not fixed to the robot. So when the robot tips forward, the water bottle tends to come off, so giving it a dynamic torque, which makes it more difficult for the system to handle. And another reason is that this water bottle is heavy enough to considerably reduce the stability of the system. Some interesting questions to ponder. The controller that we used in this experiment is a state feedback controller. We had a feedback gain, and we also had another loop for tracking the position, which was an integral controller. Now, why did we do this, and why not use another controller, say a PID controller? So try implementing a PID controller, and so how good would it be with respect to a state feedback controller, or is there a better controller that we can do, and how would you approach such a problem? Another thing which we tried out now is by changing the wheel radius. So we designed it for a particular wheel radius, and if we change the actual system, will the feedback gain still work? And as we noticed, if we have designed it for a large wheel and if we replace it with a smaller wheel, we saw that the stability was considerably less. Now, what if I replace it with a wheel of a radius larger than the one I designed it for? Will that be more stable or less stable? Justify your claim. So those are interesting questions to think over and answer. And some improvements, some extensions to this program. So a trivial extension is adding a remote control. As you saw, we were in the model, there is a speed and turn angle input that we can give. So instead of giving it as a stationary 0 and 0, we can have another NXT kit which is communicates with this kit over Bluetooth, and we can have say 4 buttons which determine what direction you want to move in. Another thing is dynamically changing loop gain. So what I am trying to say over here is that is there a way by which I can have some feedback about the weight that is on top of the robot. So say if I can give the system and the information about what weight I am going to give, can it calculate all the feedback gains on its own and automatically change the feedback gain so that it remains stable when I load it and unload it as well. And another extension would be flip up and stabilize. So what I am referring to over here is that in our experiment we had to hold the bot stable at an erect position during the calibration and release it from the equilibrium point. So can it flip up on its own from its stable equilibrium position, which is lying down? So can the wheels can you have 2 controllers? One controller flips up the bot, and then you switch to the other controller which will stabilize the bot. So these are not trivial, they are definitely challenging, but it will be a lot of fun to get these things to work. An important thing that you must keep in mind when you are trying to do a flip up controller is to verify that the motor that you are using can actually give the torque required to flip up the robot. So try experimenting on your own. So here are the references that I have used. This particular document is very extensive. Let me show you. It has all the details of what has been used in this particular system. So this is the building instructions. It has detailed instructions using photographs, which you can use to build the robot. A tiny difference is that the way I have built it is different, where I have changed the position of the wheels and I have removed the ultrasonic. This is, by the way, an ultrasonic sensor. So you can try different configurations and appropriately change the controller so that it works. And the other document, model based design, this is also this is an extensive documentation on how the controller is designed. So this is the document from where I got most of my information. It has all your state equations. It has you can check the derivation of all these equations and can get an in-depth understanding of how the states are derived and how the feedback gains are calculated. So thank you for watching. Hope you learned something good out of this. Thank you.